Hi everyone, in this video we will be talking about Watchdog timers on microcontrollers. First, I will cover some Watchdog timer basics, talk a bit about putting our micros to sleep, and then solve some practical problems using the Watchdog timer. So what do we have here? We have a very basic circuit, a blinky LED project from our previous video, and we have a PIC10F220 here. And if you want to know more about this PIC and looking for where to start, check out my previous video linked down below. And this circuit is powered by a PIC3 programmer, which is also hooked up to the circuit through a multimeter, so we can also see the current consumption as we code and as the circuit runs. The PIC10F220 is a baseline microcontroller from Microchip. It's one Aussie bucks here from well-known suppliers. It used to be cheaper, but I guess the prices affected everything nowadays. So it's a very baseline chip. It's very limited in its capabilities, but it's quite good for understanding the basics, and it has all the bells and whistles that you would expect from a micro. So I definitely recommend if you want to understand more about how microcontrollers work. It's because it's very simple in nature, it's easy to grasp some of the concepts as well. So let's have a look at our datasheet first. And watchdog timer, there you go. So the watchdog timer is, as its name suggests, it's just a timer with a period. It's independent from the oscillator of the microcontroller. So it's, has its own RC on-chip oscillator. RC stands for resistor capacitor oscillator. And when it times out, it generates a reset instruction and resets our controller. So why do we need this? There are actually two main reasons for that. One of them is some stuff might go wrong in your processor and it can go unresponsive because the watchdog timer is independent. It could just reset your micro and put it in a good state rather than an awkward, not non-working bogged state. So that's important. And the second bit is you might just want to put your micro to sleep, power down mode, and we can wake it up using the watchdog timer. So that reset will wake up the processor again. So that's good for power savings, reducing the power consumption, and hence that's why we have the multimeter hooked up to the circuit as well. So we talked about a period on the watchdog timer. As all timers, it needs to have a period. And in this particular PIC, we have something called a prescaler. It's pretty much all micros have a prescaler for the watchdog timer. Some of them has a post scaler. So it's basically a multiplier that we're going to multiply its nominal timeout period, which is, in this case, 18 milliseconds. And we configure this through the option register. Again, in this PIC, in different micros, it could be different. But in this micro, we have the option register and last 3 bits of it. We will use it to set our prescaler, and that's going to be multiplied by the 18 milliseconds to result in the desired period. So if you leave it like all zeros, then it's 1, which means 18 milliseconds. If you set it to all ones, then it's 128 times 18 milliseconds. It's about 2.3 seconds. So that's how we set up the period on the watchdog timer. So another thing is when certain things happen, we also have a status register on the this micro, as well as many other micros. So we have the timeout and power down bit. By using these bits, we can understand post reset whether a watchdog timeout has occurred or is it a power down situation, and we will have a look at it in the code as well. All right, let's jump into code. So we have a very simple blinky program here, where in the main function we set our pin as GP0 is digital output, and we are looping an infinite loop, and we're toggling our pin and delaying for 1 second. So first I'm just going to change it to 5 seconds so we can see we can get a clear reading on the current, because the multimeter is averaging between the LED on and off states, and that doesn't give us a clear reading of what's consumed by the micro and what's consumed by the LED. So it looks like when the LED is off, it's 600 microamps, and when it's on, it's like 10 milliamps. So that's good. Now we can enable our Watchdog timer. So here is the configuration bit for Watchdog timer. In this baseline 10F series, you have to enable it or disable it by the configuration bit. But in more capable micros, you can just enable it in your program as well. So our Watchdog timer is enabled now. And let's see what happens. Okay, it's all good. But it looks like now our LED is not blinking every 5 seconds. It's more like every 2.3 seconds. And the reason for that is once the PIC is reset, our option register defaults to, I'm just going to put the binary literal here, all set. And that means the last 3 bits are all ones. And that gives us a prescaler of 128. And that's multiplied by the nominal period of 18 milliseconds of the Watchdog timer. That gives us 2304 milliseconds, which is quite like 2.3 seconds. So if you look at the data sheet on the reset, you will see that after device reset, option bit in the power on reset and every other reset, all bits of the option register are set. So it's not the same with other registers. We're going to come to that. Some registers are just preserves their value, and the file registers will general purpose registers will also preserve their value. We're going to come to that. But the option register, you have to always set it. Same as the analog digital control and the trace bits, trace register, you always have to set it because they always get their default value after any device reset. Okay, now what can we do to achieve this delay again? So what is going on here is that while we are delaying for this 5 seconds, the Watchdog timer times out and resets our processor, so it goes back and that toggles the LED again. So for that reset not to happen, we have to clear the Watchdog timer. If you are doing a length operation like this, just want to reset, clear the Watchdog timer, and we're just going to use the clear Watchdog instruction for that. Let's put a loop here for loop for 5 times, and instead of delaying 5 seconds, let's delay for 1 second. So that's more than enough for it's well below the period of the Watchdog timer, which is 2.3 seconds. But then after this 1 second delay, we're just going to execute the clear Watchdog instruction. So that will reset our Watchdog timer, so it's not going to reset our processor. Let's give it a go. All good. Now we have LED on for 5 seconds and LED off for another 5 seconds. Also, we can see the current consumption clearly, it hasn't changed at all. So the next thing we can do is not delay at all, because even though the micro is doing nothing here, it's still on, it's still consuming power. Instead, we can try just executing a sleep instruction. But let's get rid of all these loops and see what we can do with using only the sleep instruction. So what we're going to do, we're going to take this bit toggling, take it out of the loop, and after we toggle the bit, we will put our micro to sleep. So that's going to put it in power down mode. And in 2.3 seconds, it will power back up, it will reset, and our pin will be toggled again. So let's give this one a try. Okay, all good. Now you can notice the current consumption when the LED is off went down to something like 230 microamps, and the multimeter is still averaging, so it's not very clear. But we will come to that in a sec. So now the next thing that we want to do is what if you want to, instead of, let's change the option rate, and instead of waiting for 2 seconds, 2.3 seconds, let's wait for 1 second. So the way we can do is that we can change our prescaler to 64. If you look at our data sheet, the option register, the Watchdog timer rates for 64 is the last 3 bits should be 110. That's what we're gonna do here. I'm just going to copy and paste this bit, and we will set our option register to, this was its default value, and we'll just clear the last bit, and that would give us a prescaler of 64, and that would be multiplied by 18 milliseconds. That would be 1152 milliseconds. So yeah, that's about a second. So let's give it a try now. Okay, now we had a period of 1 second, close to 1 second, and our LED is blinking every 1 second. It's 1 second off, 1 second on. So let's clean up this code a bit, and instead of 1 second on, 1 second off, let's code something that is more like a blink. I'm just going to put a little method here, and this function will turn on our LED first, and then it will delay for 10 milliseconds, and then it will turn it back off. So that would give us like a proper blink. And what I want to do is that instead of this toggling, we're just going to execute our blink here. So that way we're just going to save some power. Let's imagine this is some sort of a beacon application that blinks like that transmits some kind of data, or just some sort of alert every 1 second in like small bursts. Okay, programming is complete. Now we have a little blink and then a wait for 1 second. And now the next problem is, what if you want to do it a much larger value than the maximum period we can get out of the Watchdog timer? So when the device is reset with a Watchdog timer timeout, or when it's the wake up state from the Watchdog timer, there's a way to tell this. We can look at the status register that's in the datasheet. And in the status register, you can access status register by using XC8 macro status bits. By accessing the TO, and that's for timeout, and the power down bits, we can tell whether the device is reset by the Watchdog timer wake up, or Watchdog timer timeout, or any other reset, which is well explained in the datasheet. So it's a little bit limited in this micro, but there's like very similar configuration, very similar structures in all the micros, status registers, very similar fashion. So if you do it with this one, you can just figure out the datasheet for other micros too. So here I'm checking the TO bit and the PD bit of the status bits, and I'm checking that both of them are clear. This indicates we have a wake up situation. And all the other cases, we have just normal power up or some other reset. Okay. So as you remember from the datasheet, once the device resets, it's just going to keep the general purpose file registers. So we can just define some sort of a counter here, like, yeah, I'm just going to call it a counter, and don't initialize it here. But in this other reset, all other resets, you can initialize our counter to 0. And if it's a Watchdog timer wake up, we're just going to increment our counter. If it is at a certain value, in this case, I'll just say 5, then we will blink. Otherwise, we won't do anything. And at the end, we can remove this option bit because I'm going to leave it at a default period of 2.3 seconds. We will put our micro back to sleep. Okay, and one last thing, by the C standards, if you define a static variable like this, every time our program resets, it will be cleared. So we will tell the the X8 compiler basically that this using the persistent directive, you can tell the compiler, hey, don't reset this register, don't reset this variable. So it's going to preserve its value between device resets. Okay, so let's go through the code once more to see what's happening. We're setting our pin as digital IO, yeah, and then we are checking for the wake up condition. If it's the wake up condition, we increase our counter, and if our counter equals 5, then we blink. Here, we also need to reset our counter to 0. And for all other reset conditions, we're just initializing our counter to 0. 10 seconds is a little bit perhaps too long. Let's keep it to somewhere like 4 seconds. Okay, it works. It's about 4 seconds. And if you look at the current consumption now, we are down to 150 milliamps. So I'm just going to change my multimeter's current measurement to microamps. So we can see the microamps. And this is averaging. And when the LED goes on, there's a spike in the current, but when it's off, it generally stays around 30, 40 microamps. So that's a lot of power savings, and this is you can run this thing years of a battery, and it's going to be a real good application for beacon-like applications where you have to do something with long periods. So you can increase the counter, you can use multiple counters, longer counters. If you want to increase the period even further, you can go as far as you can imagine here. And if you want to decrease the Watchdog timer period, 18 milliseconds is the minimum that you can do that because it's nominal period. If you need less sleep time than that, you should probably use something else and not use Watchdog timer. And yeah, that's pretty much it. Comment below if you have any questions, feedback. Hope you found this video useful, and if so, please like and subscribe, and don't forget to have fun. Thanks for watching.